let's get started with the second vodcast on the solutions topic. Go to Roman numeral 7 in your outline and look for colligative properties. All right, colligative properties are any effect that a solute has in a solution. So the effect that salt has in water on its freezing point and boiling point and osmotic pressure, etc. So let's talk through a few of them, and we'll add some math a little bit later and get some practical experience with it, hopefully on a hot day this week. All right, let's start with freezing point depression. Anytime you put salt in water, it lowers the freezing point of the solvent. Ocean water doesn't freeze as easily as lake or creek water, fresh water, and that it is depressed dependent on only the concentration of the solute ions, and it uses the concentration molality. This is a useful property when you can use it to lower the melting point of ice when you're making ice cream, so you get a colder environment so that you can freeze the ice cream. It's also really helpful if you live in a place that has really snowy and icy roads. You put salt on the roads and it lowers the melting point so that your roads are a little bit safer. Sadly, your car rusts a lot faster too, but it's a price you pay for safety. All right, Mickey's wondering what molality is, because that's not one that we've spent much time talking about. Goofy knows that it's the moles of solute per kilogram of solvent. That's important, that it's not moles of solute per liter of solution, because that's more of a percent. It's part out of whole, whereas this is just comparing solute to solvent. And that's important to what a colligative property is and how it impacts the freezing point and boiling point of water. We'll come back to the math a little bit later, though. Let's keep talking about what's happening in colligative properties. Okay, another colligative property is boiling point elevation, which can be really useful when you adding a little salt to your water when you make your pasta, and that boils a little bit hotter and cooks a little bit faster. So for aqueous solutions, this means that the standard boiling point is greater than 100 degrees, assuming you're at standard atmospheric pressure like we are here in Marin County. The solute must be non-volatile. That means it doesn't evaporate easily. And the amount it's elevated depends, again, on the molality. Another situation that's really helpful is in your car's cooling system. If you use just water in your radiator, that water can boil easily and it can freeze pretty easily under normal conditions. So you add an antifreeze so that it boils at a higher point and freezes at a lower point. And then you don't ruin your car. All right, now why does this happen? Okay, let's look at some particles. We talked a lot in the last unit about what boiling point was. It's when the vapor pressure from a solution equals the atmospheric pressure above that substance. Sorry, not solution yet. Now, when you have a solute mixed in with your solvent, there are competing attractions. And so not only is the water attracted to water, but it's also attracted to particles such as salt or sugar. And these particles are literally in the way in the surface so that the water particles aren't allowed to evaporate as easily. So you have a lower vapor pressure whenever you have a solute dissolved in the water. That lower vapor pressure means it takes more energy to get the vapor pressure up to equaling the atmospheric pressure. Therefore, you have a higher boiling point. A similar thing occurs when you think about freezing. These solute particles are literally in the way of water particles coming together and making that ice crystal that they need. They're attracted to the salt particles. They're also attracted to the water particles, and the salt gets in the way, and so you have to remove more energy to get them close enough together for them to freeze. All right. Osmosis is another really cool colligative property, and it happens when a semi-permeable membrane is between two liquid substances. Semi-permeable membrane has small openings so that some particles can get through and some particles can't. Water particles are really small, so they tend to go through most semi-permeable membranes. The most important semi-permeable membranes that we are impacted by are cell membranes, and water can go in and out of those cell membranes. So osmosis is officially the flow of solvent molecules through a selectively permeable membrane driven by concentration differences. That's called osmosis. So in a situation like this where you had water on one side of the membrane and sucrose on the other, maybe a thick syrup or something, the water would flow into the sugar to try to balance out the water concentration. It will always go from high concentration of water to low concentration of water. One fun example of this is if you've ever stayed in the shower or the bathtub too long, you get what I used to call grandma fingers or pruny fingers. It's where water has absorbed into your cells and your fingers or your toes, and it's puffed them up so that they look a little bit pruny. Another cool way of using this is something my mom used to do. When we would have cookies that would get dried out and hard, she'd put either a slice of fresh bread or some apple slices in with the cookies, and within a few hours, the water had left the fruit or the bread and absorbed into the cookies. High water to low water, and then you had nice soft cookies again. Great hint. All right, so we're getting ready to do the math. So freezing point and boiling points depend on the molal concentration, which is moles of solute per kilogram of solvent, and the nature of the solute, whether it's ionic or whether it's covalent. And they have also depend on the molal freezing and boiling point constants. A 1 molal solution lowers the freezing point of water always 1.86 degrees Celsius. Doesn't matter what the solute is, it always lowers it by that much. And the equation is right here. The freezing point depression is dependent on that constant, the freezing constant for water, times its molality, times I. I stands for the number of particles after the solute is dissolved. So that's why it depends on whether it's ionic or covalent. For instance, down here you have a glucose molecule. That is a covalently bonded molecule that does not break apart in water. So in this case, I would equal 1. Sodium chloride breaks into 2 particles. I would equal 2 because now the effect of the molality is doubled because 1 molal of NaCl has 2 particles. If you have CaCl2, what do you think I is? 3. Excellent. So now let's try out the math. Oh, first, for boiling point, the molal constant is only 0.512 degrees Celsius per molal. It's harder to impact the boiling point than it is the melting point. All right, so here's our problem. If we put 85 grams of sodium chloride in water, 392 grams specifically, what will be the boiling point and freezing points? I will be 2 again because it's NaCl2 particles. All right, so we want the K values, we want the molality, and the I. We know I is 2. Let's find the molality. We know that we have 85 grams of NaCl in 392 grams of water, which is a solvent. Hope my handwriting's getting a little better. It's hard on this tablet. Anyway, thanks for bearing with me. Let's do some conversions. We need moles per kilogram. So let's change grams to moles first. 1 mole of NaCl is 58.5 grams of NaCl. Okay, now 1,000 grams of water equals 1 kilogram. It's actually true for grams of anything, but we're dealing with water. When you calculate, you should get 3.71 molal. All right, now we can apply that to the freezing point change and the boiling point change. So let's do the boiling point since we have the equation right here. 0.512 for K, 3.71 for molality, and 2 for I. Okay, put that in, get an answer. Do the same for freezing point. Delta T of freezing has a constant of 1.86. Molality 3.71, and I is 2. Pause until you get an answer. Your freezing point should have changed by 13.8, so it's 0 minus 13.8 to get your freezing point, and your boiling point should have changed by 3.9 degrees Celsius, raising it to 103.9. All right, finally, a couple more examples of mixtures. We have been talking about true solutions, things that dissolve completely and have very, very, very small particles. True solutions are when ion is dissolved in water or small molecules like sugars. But you can also have bigger particles that stay mixed in solution for a period of time. If you have a colloid, you have some larger particles or molecules, such as a fat particle or protein particles. For instance, mayonnaise or ketchup. Most of your condiments are colloids, things that stay suspended for a long period of time. And a suspension are really large particles that you can shake it up and mix it, but they settle to the bottom, like your orange juice. Or if you remember that bubblegum flavored medicine you used to take as a kid when you got an ear infection, that you always, it says shake before using, because you have to suspend the medicine before you take it so you get enough. So the particle size varies. For a true solution, it's 0.1 to 1 nanometers. If you remember, a nanometer is 1 times 10 to the negative 9th meters. Really small. They are small enough that they cannot reflect light when light goes through it. So the Tyndall effect, which you can see here, if light goes through a true solution, the particles are small enough that you can't see the light reflected in the solution itself. But if the particles are larger, above 1 nanometer, then you can get that light showing through, and that's called the Tyndall effect. A colloid will show the light through it. A suspension the light will be reflected through it. At over 1,000 nanometers, the particles are probably too large to stay suspended for very long, and so they fall back down into the solution. So a true solution, again, does not show the Tyndall effect. A colloid and a suspension do. Now I put this on this lovely sunset backdrop because the sunset is a great example of particles in the air having an impact on the properties. I don't know if you've noticed, but when you're in locations that have higher pollution rates, more smog, you're going to get a more colorful sunset. The silver lining, as it were. And here's one last slide to help you understand why that is. So, when light comes through the atmosphere, it encounters some sort of particles. There's always dust or water molecules or whatever. And light is scattered into the rainbow of colors. You also have, other colors in here. But red is, I don't like those, sorry. Red is refracted or bent the least. It's the color that stays the most directly coming from the sun rays, whereas blue is refracted the most. And so the blue light gets scattered more, and during the day we see more of it because it's scattered from many directions. At night, when the sun is at this really low angle, we only get to see the red light. So there it is. With that, please don't forget to fill in your summary form online, and I hope you have a wonderful weekend, and please don't forget to treat your mothers well on Mother's Day tomorrow. Bye.